Okay, so in the previous video, we looked at this example of a multi-step synthesis problem. We started with ethene, and we ended up with 2-bromopentane, and we went through a series of steps in order to get to this product. So the very first thing we said, we had to elongate the carbon chain, and then we had to get rid of the triple bond, and we had to put a bromo group onto the molecule. So what we did is that we elongated the carbon chain by using propyl bromide, because we had to add 3 extra carbons onto the organic. And then we added HBr onto the molecule, and that converted it over to an alkane. And then we turned around and got rid of the double bond by adding H2 and platinum to the molecule to change it to an alkane for us. But the problem is that there was more than one way in order to get to this product down here at the bottom, which was 2-bromopentane. We just chose one route, but there is another route, and there's another way that we could have done it. So let's take a look at maybe another option or another order that we could go through in order to get that final product that we're after. So we started with ethene, and we wanted to know what can we add to it in order to get CH3, CHBr, CH2, CH2, and CH3. So 2-bromopentane. Well, first, almost every single time in these examples, if you realize that the carbon chain needs to be elongated, you do that elongation step first. There's no really exceptions with that. Most of the time, if you elongate the chain, you do that step first every single time. So the very first thing that I'm going to do again is to add NaNH2, sodium amide, in order to create this acetylide ion for me that we can then elongate. And then we can do the elongation step, and we can add 3 extra carbons, so CH3, CH2, CH2Br, and that will elongate the carbon chain for me by 3 carbons, so 1, 2, and 3. Now, in the previous video, what we did from this step is we added HBr, and we got bromo onto the molecule first, but you didn't have to do it in that order. You could have actually switched the order of the second and third step and still get the same answer. So we could, if we wanted, to take that product, that alkyne product now, and we could add H2, but we can't add H2 and platinum, because if we add H2 and platinum, what would happen is that this triple bond would be completely destroyed to a single bond, and then there would be no way at this point that we know of to add bromine onto that molecule. So we have to keep a bond in place, some form in some fashion. So we don't want to destroy the triple bond character down to a single. What we do want to do, though, is get rid of that triple bond, and we can convert it to a double, and we do that by using Linlar. So H2 and Linlar would be an acceptable second step if that's the route that you would want to go with. And what would happen is that the triple bond would change into a double. So we would see 2 hydrogens, one on each side of the carbon now, and CH2, CH2, and CH3. Now that we have this alkene, well, we can play off of that double bond character now and go back and take a look at all of those alkene reactions and figure out, well, we've got this double bond, we need to put a bromo onto that organic. How can we put a bromo onto that organic? Well, we add HBr just like we did previously, and H plays with other H's because this is a Markovnikov reaction. So H will go on the left here, and we will end up with CH3. This double bond would break into a single, and my bromo group would go onto the right-hand carbon, so bromo would go there. So H goes to the left, Br goes to the right, and then the rest of the molecule, of course, does not get touched. So this is another acceptable plan in order to get to the product that we're after. So in the previous video, we elongated the chain, And then with the triple bond, we added HBr in the second step to put the bromo group on. And then to get rid of the double bond, we added H2 and platinum. Well, in this video, in this example, we can do the same exact thing, elongate the chain, but this time use H2 and Lindlar in the first step to take it to a double bond, and then play off of the alkene reactions and add HBr to the molecule to have it brominated. So either one of these is fine. Whatever you decide to choose, that's perfectly up to you. You can do whatever you need to in order to get, as long as it makes sense, chemical, organic sense, you're more than willing to use any reaction that you want in order to get it done. Now, there is another option, a third option here. Not really an option though, but it could be a choice that you would consider before you realize the problems that go on with this route. So let's take a look at what that other choice might be. Okay, so here we get the same reaction. What kind of reagents can I do in order to get this product? Well, again, chain elongation typically happens first. Well, I could, if I want it to be creative, to take this acetylene and add NaNH2 to it to get my acetylide ion. And then I can take this acetylide ion and elongate it. And I'm going to elongate it, but not by 3 carbons this time. Let's just try 2 carbons and see what happens. So let's do CH3, CH2Br. Okay, so when that elongates, what I'm left with is a carbon, triple bond, carbon, and now I need to add 2 carbons onto that because of the ethyl bromide. But this is not a 5-carbon chain. But that doesn't mean I can't elongate again. I could actually take this and elongate a second time. So I could take it and add NaNH2 all over again, and I could create an ion on the other side of the carbon, right? We've got rid of this hydrogen, and we put an ethyl group on it. Why can't we get rid of this hydrogen? Well, we can. So C, triple bond C, CH2, CH3. Well, now that I've got that new acetylide ion in place, I can elongate it again. Well, I need 1 extra carbon here to give me a 5-carbon chain. So I could bring in methyl bromide if I wanted. And this would put a methyl group onto the left, carbon, triple bond, carbon, CH2, CH3. And this gives me an alkyne that I can then react in any which way that I want in order to get a bromo group on there. Well, I could take that molecule and I could add H2 and Lindlar if I want to keep it the same as this example here. And when I do that, I would end up with CH3, C double bond C, CH2, CH3, and then that triple bond was broken to a double, so H went on one side and H went onto the other. And then I can add HBr to this molecule and convert my double bond into a single. So CH3CH, and then there's a double bond there, CH, CH2, CH3. The HBr would break this double bond to a single, and 2 sites of attachment would open up. H goes on one side, Br goes on the other. So Markovnikov rule follows here. Well, hydrogen has a choice. It could go here, or it could go to the right. So I'm going to have to show that choice. And that's where the problem lies within this mechanism route. So if H goes on to the left, Br would go on the right-hand carbon. If H goes on the right, Br would go on the left-hand carbon. So I would get 2 choices here. So if we wanted to name them, this would be 3-bromopentane, and this one would be 2-bromopentane. So the problem with this mechanism route is that you do get the product that we're after. You get the 2-bromopentane, and that's what we needed. However, you also get a mixture, and the mixture will have 3-bromopentane in it as well. and that mixture we might not want. So this route, even though it gives us the 2-bromopentane, is not the best choice because sometimes we'll get 3-bromo version and sometimes we get the 2-bromo version. The other examples, we got 2-bromo only. So the other routes were a little bit better choice.